Everyone, welcome back. Today I'm going to explain a problem on design for shear. A double T section used as a bridge girder is made up of flange 1200 mm wide and 150 mm thick. The ribs are 150 mm wide and 1500 mm deep. The section is pre-stressed by high tensile wires of area 4700 mm square, located at 850 mm from the soffit of the girder. The stress in the wire is 1200 mm square. Take FCK 40 Newton per mm square. Estimate the ultimate shear strength of the support section. They have given a T section, but it's a double T section. So this diagram is not given. We should write two T sections here. The complete width of the flange is 1200 mm and its thickness is 150 mm. You can see here I have mentioned the thickness as well as the width. Next is about the rib, or it is also called as web. The width is 150 mm and the depth is 1500 mm. The section is pre-stressed with the tensile wire of area. We will see that, but whatever we require for the diagram, I'm reading that. It is located at, we have a cable. So I have mentioned these cables here. It is located at 850 mm from the soffit of the girder, from the bottom to the center of the cable. Soffit means it is bottom. So from the bottom to the center of the cable, it is 850 mm. The stress in the wire is 1200 mm and we should calculate ultimate shear strength of the support section. Like this we should write a diagram. So let's see the calculation part. I have written all the datas. That is, area of cable is 4700 mm square and this is a pre-stress 1200 Newton per mm square. Next is pre-stressing force. This is initial pre-stress. This is pre-stressing force is stress into area of the cable. Stress is 1200 into area of the cable is 4700. That will give you the pre-stressing force as 5640 kilonewton. FCK 40 Newton per mm square, and while taking the width you should be careful here. This is width of the web. For width of the web I have changed the notation. That is BW is 150 into 2. You can go back to the diagram and check the value. We are talking about this 150 as we have 2 T section or double T section. We should consider both T section web width. It will be 150 into 2. That will be 300 mm. Next is overall depth. In the question they had given about the depth of the web or rib, but we want overall depth. Complete depth is required. For that 1500 plus 150 will give you D value as 1650 mm. These are the basic data we should be writing. Next is the calculation of FT, where FT is nothing but maximum principal tensile stresses. If FT value is given in the question, then directly take that, or else you should use a formula as 0.24 into root of FCK to calculate FT value. FCK is given, that is 40. You will get FT as 1.517 Newton per mm square. Next is FCP, that is compressive stress at centroidal centroidal axis due to pre-stress. That is calculated by FCP is equal to P by A, that is load by area. We have already calculated pre-stressing force. So 5640 into 10 power 3 whole divided by the area. While calculating the area, be careful. The first term you can see here is 1200 into 150. That is the flange area. 1200 into depth is 150. This is the area of the flange. Next is about the rib area. To calculate the rib or web area, you should take depth into width. That is 1500 into 150. That is area of one rib. As we have two rib, we should be taking it as 2 into 1500 into 150. Therefore, FCP is 8.95 Newton per mm square. Now we know all the values. We can use those values in the formula. VCO is equal to 0.67 B into D into whole root of FT square plus 0.8 FCP into FT. Substitute the value 0.67 into 300 into 1650 into whole root of 1.517 square plus 0.8 into 8.95 into 1.517 is a value. So we will get VCO has 1203.25 kilonewton as a value. Okay, like this we can calculate ultimate shear strength at the supports. Hope you have understood. Thank you.